This talk about the generalization ability of deep learning methods is based on the paper Shortcut Learning and Deep Neural Networks and is supplemented with other sources. All references can be found at the end of the presentation. We will talk about what shortcut learning is, how it happens, and how we can solve it. Due to time restraints, we will mostly talk about high-level concepts instead of giving a comprehensible list of specific technical solutions. We will also brush against the design question of whether shortcut learning is a failure. For ease of illustration, most examples come from the realm of image recognition, but we will see that shortcut learning affects all areas of deep learning. Let's start with a simple example. We train our DNN on cow images like this. Afterwards, we tested on new images of cows with different colors and patterns, and the model classifies them correctly, just like a human being would. Since the model doesn't seem to rely on texture or color that much, we've probably succeeded in creating an object classifier that recognizes shape, right? But later, we try it with a new image, and this time, the model fails. It's very confusing, because the cow itself is nearly identical to our training data. The only real change is the background. And that's exactly it. Never mind shape recognition. Our model didn't learn anything about cows, except that they tend to appear near grass. In the worst case, it will label an image as a cow without one being present at all. And there is an example of shortcut learning. It means that the intended strategy of a model, shape recognition, is different from the actual strategy, in this case looking at the background. However, this isn't actually a learning failure, but a communication issue. We often have clear strategies in mind. Strategies that are defined by our understanding of the world, so objects and depth perception, etc. Computers, however, not only have a fundamentally different understanding, but they also get access to data in a limited fashion. Instead of seeing our 3D world, they can only look at pixel arrays with reduced colors. Those differences mean that we cannot tell a computer what we want directly, and instead must find a workaround. But framing good goals is hard, even when it sounds easy. Reinforcement learning of video games should be trivial. After all, the rewards and punishments are already included in the game in the form of points and losing. Just use this framework and it should be fine, right? However, Dr. Tom Murphy VII trained a model to play Tetris and found that it failed in two interesting ways. First of all, it played erratically, seemingly to get points as quickly as possible. Second, if it noticed that it was about to lose, it paused the game forever. While this solved the issue of losing, this solution was different from our intended strategy and from our goal to make the model play the game. This is obvious to a human, but a computer doesn't have access to these invisible assumptions. While communication issues like this can be frustrating, there's a reason why they're worth it. Because the problems we want to solve are too complex to be coded directly, making machine learning the best tool for the job. The complexity, however, means that we often don't know what happens in the black box that is a neural network. We just feed it inputs and get predictions as a result. And while we can manipulate the learning process, understanding what exactly the model learned is still hard. Especially if we look at it through the lens of anthropomorphism. We are very susceptible to humanizing the world around us. And while neural networks are inspired by the human brain and share, as we will later see, many similarities, assuming that computers solve problems the same way we do is harmful both for the analytical process and for our ability to debug efficiently. To counter this, the paper proposes to apply an adjusted version of Morgan's canon to machine learning. The canon originally applies to animal studies and says that we should not assume a complex solution if a simpler one is just as effective. In our case, we should not assume that our model learned to recognize shapes, unless we can guarantee that it didn't solve it in an easier way, for example by checking pixel position or color, or maybe even relying on file size. Choosing the easiest way isn't the model being lazy, it's a symptom of it working as intended. After all, human beings also make decisions based on easy, potentially superficial features. We don't perform a DNA test or weigh the object in question, we just look at it. It's easy and successful. But what is easy for a computer? Similar to how our world experience is shaped by nature and nurture, a model is defined by its architecture training data, loss function, and optimization. All of this combines to the inductive bias, also called learning bias. Without this bias, our model couldn't make any decisions. So if we want to change how these decisions are made, we can adjust any of those processes either by using subtle tweaks or preventing shortcuts by blocking them manually. Adjusting the training data might seem especially promising. After all of this shortcut problematic just sounds like overfitting, doesn't it? It should be fine if we just add more data. However, training the model on 1,000 more images of cows and grass does not actually discourage it from using the shortcut. If anything, it cements the grass as a very informative feature. While solutions for this specific toy examples could be found by manipulating the data to include different backgrounds, this is not actually viable with most real-life data. That is because we have a dataset bias. Our dataset contains correlations that occur naturally, but might not make good decision parameters. And once data gets complicated, for example with user profiles and recommendation systems, manual change might mean trading one bias for another. Either way, just tweaking the training data is unlikely to prevent shortcuts from occurring. This isn't to say that context doesn't matter. In humans, we call this contextual bias. Have you ever met someone in public that you just knew, but also couldn't place? And then suddenly it hits you. It's the barista from the coffee shop you visit every day. While this person should have been instantly recognizable, the change of context was enough to throw us off. These are only momentary lapses, however. If you woke up to a cow standing over you, it wouldn't matter that it's in your bedroom or that it looks very odd. You'd still recognize it, no matter how sleep-deprived you are. So how do we do that? We rely on multiple senses and aspects: shape, color, texture, context. This way, our prediction ability is unlikely to be swayed by a single oddity. In humans, we call this Q combination. The equivalent in machine learning is feature combination. It means that our model will consider multiple features in a nonlinear fashion so that they don't cancel each other out. In contrast, discriminative learning picks a single successful feature and discards all other data. In the worst case, it's an uninformative feature like the color of a single pixel. This might do well during testing, but not with new data. And it's also the reason why feature combination alone doesn't necessarily defeat shortcut learning. Nothing stops the model from choosing multiple bad features. But what if we could? We might be unable to understand what's happening in the black box, but we can make it report to us in a comprehensible fashion. This knowledge of the conceptual level makes it possible for us to debug the learning more directly. The drawback is that sometimes we need performance that is better than a human being's, or that the data connections are too complex for us to understand. By forcing human strategies on the model, we might trade effectiveness for readability. An example for unintended, uber-human performance is when the model recognizes too much. In this case, we learn about potential shortcut learning not from a failure to generalize, but by noticing that the model classifies images that should stay unlabeled. Let's look at this guitar. Our model manages to classify it without issue. However, when we show it this abstract pattern, it also sees a guitar. That's because while training, our model notices that this curve is a very reliable feature. So when we show it an image full of curves, we get a false positive. To find instances like this, we have to extend our testing method. Traditionally, most models use IID testing. IID stands for independent and identically distributed, and means that our testing set comes from the same distribution as the training set. Contrast this to out-of-distribution OOD data. Our initial data is like a puzzle piece of the whole distribution. The OOD data is another piece and likely to show different idiosyncrasies. You can imagine it as taking photographs on a different day, or running an image generator with a new seed. OODs can be split into two categories. Group 1 are the natural OODs. They weren't part of our training data, but it could have been. While these images are natural, they can still be tricky. If we had a brown cow on rocks, the model would be challenged to differentiate the object from the background. Group 2 are synthetic OODs. They are artificially created images or adjustments to existing data that are meant to trick the model to reveal shortcuts. One synthetic method are adversarial examples. They are model-specific worst-case scenarios. The idea is to change the sample a tiny amount, for example by offsetting it a few pixels using a vector field, and produce a prediction that is both wrong and made in high confidence. To humans, the result is often barely indistinguishable from the original, which really shows the difference in strategies. Another popular technique is the Q conflict stimuli. You combine one intended and one unintended cue and see if the model still works. Mixing textures and shapes is an obvious application, but it can also have more subtle forms, like taking the low-frequency details from one image and the high-frequency details from another. However, it is important to remember that you train on a specific distribution on purpose. In his book, Deep Learning, Andrew Glasser describes that training a model on animal patterns is not enough to recognize the animal itself. If the user provides an uncropped image, it is very likely that the model will get confused by foreign patterns. That makes sense. It's not what you trained your model to do. Our guitar is similar. Since our model was trained on natural images, it also assumes that the new data comes from the same distribution, object-based reality. Under those conditions, is it really that unreasonable for the model to assume that the image depicts stacked guitars? So knowing all this, what is shortcut learning? Shortcut learning means that the model employs a strategy that wasn't intended. These shortcuts often go unnoticed if the model is only tested on IID data. Once new data is introduced, those shortcuts often surface. Shortcuts can lead to different failures, either by not recognizing new data or being very confident in predictions that make no sense to humans. Shortcut learning happens mainly because it's just part of the nature of deep learning. Both the human brain and neural networks prefer going the easiest way. What easy means is defined by the inductive bias. Shortcut learning can also happen because of architectural issues, like discriminative learning, which discards possibly valuable inputs. Often our dataset is at fault too. Sadly, we cannot combat natural occurring correlations directly, or often even notice it in complex or big datasets. We can, however, notice the shortcuts our model employs. Since shortcuts are the most harmful when undetected, it is advisable to check for them, even if you don't plan to act on that information. Getting a better understanding of the coverage and limitations of a model is always helpful. One way to do that is to introduce ROD testing deliberately instead of waiting for the model to fail after it's been deployed. There are different ways to create appropriate ROD data, and depending on the topic, existing collections might be available. We can also force human readability on our model, making it possible for us to detect shortcuts manually. This step is especially useful when we have a clear strategy in mind, or when the model is used to make decisions of high importance, so that we aren't at the mercy of a possibly flawed system that we don't understand. Once we have detected the source of our shortcuts, we can take steps to prevent them from happening. The specifics depend on the issue, but in most cases it boils down to influencing the inductive bias, and thus how the model sees the world, or by forcing it to not employ specific shortcuts by blocking them off in code. It's likely that domain knowledge is necessary. Preventing shortcuts is an active area of research, and people are approaching it from multiple angles. We are also still in the process of understanding neural networks in general, and each insight into that also benefits studies about shortcut learning. Until then, there are design issues we can think about. How do we formulate goals that hold firm against loopholes? Do we want to imitate humans, even in areas where we might want superior performance? And if not, how will we make sense of uber-human decisions? Either way, I'm looking forward to future developments. Thank you for listening.